Okay, we have very quick review. Proper time. Proper time use delta TP. So the proper time is time measured by someone who see the two events at the same location. Uh, okay, the two things happen at the same location. Uh, the proper time always shortest time measured by anyone. Uh, to look at this example, we have pendulum uh, go back and forth and has time period equals 3 seconds. Start from here, go that way, and come back. Uh, well, now at the same location, right? So because pendulum on the Earth, so on the Earth you measure proper time equals 3 seconds. Now from spaceship, uh, okay, moving at 95% of speed of light, uh, this measurement from spaceship is not proper. Uh, it turned out to be 9.6 seconds. So now, if I ask you the pendulum was inside of a spaceship, then what happens? Now the time you measure in that spaceship is going to be proper. Uh, okay, so we will have chance to discuss other example. Now the second uh, conclusion from special relativity is the length contraction. Uh, the length contraction, uh, time dilation, time become longer, and the length contraction become shorter. So length contraction is the measured distance between 2 points, depends on the frame of reference. Now, the proper length, I will use LP. LP, proper length, is length of the object uh, measured by someone who is at rest to the object. Uh, who is at rest to the object. Okay, so the proper length always longest length measured by anyone. Okay, so let's assume you have a ruler. Uh, ruler, let's just say the ruler inside of an airplane or inside a spaceship fly this way. Okay, so inside the pilot measures the size called the proper length, right? Because he is at rest to the object. So now, if we measure from the Earth, we see the rulers flying. So our measurement is not, because this ruler is not at rest, not at rest. Okay, so now we're going to discuss what's going to happen again, the length contraction and proper length. The length of the object measured by someone who is at rest to the object. Okay, so of course this thinking, a thought experiment. So we assume we have a spaceship travels from star A to star B. Okay, between the two stars. Uh, so of course we assume it's constant speed. Start from the from star A, the speed already is constant and keep same speed all the way. We assume again is 95% of speed of light. Okay, so now from star A to star B. So to someone on the Earth, for us, for example, the distance from star A to B, of course, is fixed, right? It's at rest. So the star A to star B, that distance its proper length to us, uh, so to an observer on the Earth. Uh, but the time is not proper uh, because uh, the spaceship starts from A and at B at a different location. So now, okay, for this measurement, the distance of the length is proper length. The time not proper to us, to someone on Earth. Uh, so now the proper length, the distance equals what? Equals speed of a spaceship times delta t. See, this is not proper, but this is proper. So now, for someone inside a spaceship, the time measure is proper, right? Because uh, he see the star A pass, then star B pass. So he claimed the two stars pass him at the same location. Uh, so he inside the spaceship measure proper time. The distance is not. Distance is not because this distance is not fixed, not at rest to him. He can even think, okay, star A fly to me, then star B pass to me. So for someone inside a spaceship, the time measurement is proper time. The distance is not proper length. Okay, so now he measured, the pilot measure distance equals v. Well, they have to agree something. They agree the speed is same times delta tp, proper time. Okay, so now, so we plug in the number. So v times delta tp. Okay, then we use the convolution we studied last time for proper time. Delta tp equals delta t times square root 1 minus v squared over c squared. Okay, so now the v times delta t give you proper length. So then we have this equals proper length times square root. So finally we combine this and that. We have the equation for proper length. So L equals proper length times square root. Remember, under square root, this is always smaller than 1 equals 0.9, 0.8, 0.7. So proper length times some number smaller than 1 will give you a shorter distance, right? So that's why we see the proper length is longest distance, longest length. The proper time is shortest the time. That's two important conclusions. Okay, so let's think a little more. Okay, so that's the spaceship. Go from star A, well, we choose Earth now, to star B. So this is the next star close to us, 4 light years away. So assume, of course, speed is constant. So we both agree speed of time equals 0.95 c. Okay, so now see what happens. So now you think about the time inside of the spaceship is proper time. Okay, so proper time is shortest distance, shortest time. Sorry. Okay, so then the speed times the time give you distance, of course, shorter too. Because speed is the same. If time is shorter, the distance is shorter. Okay, So pilot think he travel shorter distance. Okay, the proper time to ask someone on the Earth is longer time. Okay, so we see the spaceship travel longer time, but we agree the speed is the same. So longer time, of course, travel longer distance. See, uh, that's the time uh, contraction. Sorry, the length contraction. Uh, okay, so the distance for us, uh, okay, is proper length uh, because these two are fixed, always there. Okay, so that's the example help you understand length contraction. You can read it again and think about it. So when we first time study special relativity, always feel a little, well, confusing. Okay, but after you think a few times, well, uh, everything will make sense to you. So now we're going to try this example. Okay, we have okay spaceship at uh, 4,350 kilometer altitude, moving down to the Earth. Uh, so, well, this distance, by the way, is proper to us, right? Okay, so spaceship start from that point, goes down to the Earth. Uh, so this distance for us is proper length. Okay, so assume this time the speed is 0.97 c. That's measured on the Earth. Okay, so now, so what's the distance measured by a pilot inside spaceship? For us, the distance is this long. The proper time equals 4,350. And what is the distance, the length for the pilot? Okay, so use this equation. L equals proper length times square root 1 minus v square c square. Okay, so LP is given, uh, then 1 minus, okay, 0.97 square. Again, c square canceled. C square here and c square there canceled. Now this is a very simple calculation. The answer give you 1,058 kilometer. So the altitude for us is 4,350 kilometer. And the pilot thought, okay, well, it's not that high. It's only 1,058 kilometer. So that's relativity. So the length contraction. So now a same example. So if you have a textbook, you can read and try the problem again. So suppose, okay, uh, the spaceship is 267 kilometer from the Earth measurement by the pilot, and 625. Okay, so now, okay, so the pilot measure 625 kilometer. Okay, and from Earth it's 267 that height. Okay, so now how fast is the speed of spaceship? Uh, so here's a similar, but ask you different question. So now the height from Earth to the spaceship. Okay, and for the pilot, by pilot, he thinks 267 kilometer. And from the Earth, measure on the Earth, we think is 625 kilometer. Again, we have the proper length. Okay, so now what is speed of spaceship? So now let's see. So we use same equation. L measured by pilot, LP measured on the Earth. So we plug in the number 267 and the proper length from Earth to 625. Then now this time we want to solve for B. Okay, so how we can solve this? Now it's just mathematics. So if I solve this, well, we want to cancel square root, right? So we're going to square both sides. So 267 square times 625 square, then the square root cancel. So now you know how to do it. You open parentheses and solve for b. Finally, the answer should be give you here. So the v equals that's speed of the spaceship 0.904 c. C speed of light. Again, when we solve problem for speed, well, we always use the unit of c. 0.9 c, 0.8 c, 0.75 c. Okay, so now I give you more examples here, and if you have time, you can also try those homework assigned. I will give you answer the solutions later. Okay, now next conclusion. We're going to study speed. We call relative velocity in special relativity. Okay, so now the notation you have to pay attention. Let's take this as the example. Let's say a vehicle. The vehicle has speed. Suppose 0.8 c. We don't have such fast vehicle. But you know, the reason we study special relativity because we want to study a high-speed motion. So now on the Earth, okay, then here vehicle, and from vehicle you throw a baseball. So suppose the baseball is 0.7 c relative to this vehicle, motorcycle. And 0.8 c is speed of motorcycle. Okay, so now we have different speeds. We need to give definition and notations. So we're going to use U prime. U prime. So U prime is velocity of the object, the baseball, measured in a moving frame from motorcycle, for example. So U prime equals which one? This one. U prime equal 0.7 in this example. So U prime is velocity of object measured in a moving frame. Now U is the velocity measured on the Earth. To make things simple, we choose Earth always like stationary. And of course, you can choose another way, relativity, right? You could choose, okay, you say the vehicle stationary. Or then, well, this guy going to moving backwards this way. So anyway, we assume the Earth is stationary for this example. So the V, I'm sorry, the U is velocity of the object measured on the Earth. Okay, so now the vehicle go 0.8 and throw a baseball 0.7. So to this guy on the Earth, do you think it will be 1.5 c? Well, that's impossible, you know, because nothing can go faster than speed of light. Then what's going to be? We're going to discuss. So last one, the V is velocity of the moving frame. That is speed of the vehicle. for this example be zero point 0.8. So this problem, the v equals 0.8, that's a moving frame relative to Earth. The u prime is velocity of the object measured from the moving frame, so that's 0.7. Baseball, 0.7 c relative to vehicle. The u is the speed measured by someone from the ground. Measure the speed of baseball relative to ground base. Okay, so classical velocity addition. We know this one is not correct for high speed motion. Okay, so for low speed is still no problem, but for high speed, what's going to be? So we call the velocity of relativity. We have this equation. Look a little complicated. So this is a very important one. So now the u equals u prime plus v. Divide by 1 plus u prime times v divided by c squared. Okay, again, so the v, let's look at the example. The v is the speed of the moving frame relative to Earth. And u prime is the speed of object relative to the moving frame. Okay, like baseball relative to the vehicle. Okay, and now u is, we can call the speed or final speed. The speed of the object relative to the Earth space. Okay, so remember which one's which. Why we should use this one? Is this one right? Well, okay, so now we have a two rule. Number one, so if the speed is very low speed, well, compared to speed of light, so this equation must be reduced to the classical one, right? Okay, so we're going to check that. At low speed, so this equation is going to reduce to classical. Now at high speed, okay, so if you turn on a light, okay, suppose this vehicle at 0.8 c and turn on the light, so what speed of light is a c. So now if you measure from the Earth, it still should be equal to c. No matter how fast this vehicle is moving, the speed of light still should equal speed of light. So now let's check. So first of all, let's say if the object is at a low speed, say less than 0.1 c. Okay, so the objects were slow compared to speed of light. So now we can think the u prime, right? This object relative to the moving frame much smaller than c. Okay, so if that's so, then this term almost equals 0, because at low speed, either if the vehicles were low speed, like an airplane, okay, all the objects were slow, then divide by a big number and a square, c squared. So this term almost equals 0. Okay, see, so this term equals 0. So now denominator equals 1. Okay, this part is going to equal to 1 because this almost equals 0. So then what do we have? Classical result. So this equation is correct. At a low speed, reduced to classical. So now let's see high speed. So now suppose you have a light beam is emitting from the moving frame. For example, can be airplane or spaceship, anything. Uh, so now you send a light. Uh, so U prime equals C. Because U prime is the speed of the object relative to moving frame, which is light, so speed equals c. So now see what happens. We're going to use this equation. Now the u prime equals c. So u prime equals c, u prime equals c. So you plug in c and c and c squared. Okay, so now we just do little mathematics. We times c divided by c. Okay, up and down both times c. I just want to simplify. Okay, so this c I'm going to leave there. Now see this c times this term here will give you c plus v because this cancel. So then what do we have? This c is still there. This c times denominator. So the top we have c plus v, the bottom c plus v, then times c. So of course this be cancelled, give you c. So that means if you turn on the light from airplane and from a spaceship, and we measure from the Earth, we still find same number, still equals speed of light. So this equation work very well. Okay, so now we have two examples. The first example, we're going to just use some number for what we discussed when you turn on the light from the spaceship. So we have vehicle moving at 90% of speed of light and emits a laser beam. Of course, that speed equals speed of light. So now we want to find the speed of the light measured by someone on Earth's surface, in Earth's frame. Okay, so you send the light from a vehicle. What is speed we measured from the Earth? Okay, so for this example, the v equal 0.9 speed of vehicle. Then u prime equals c. This is the speed of light from the vehicle. And we want to find u equals what? What we measure from Earth's surface. Okay, to plug in, use that equation. So now the u prime equals c. Equals c. Okay, and the v, speed of vehicle equal 0.9. We just plug in. Okay, you see that the c plus 0.9c, 1.9c. The bottom, c squared and c canceled, right? So that's the c squared canceled with this one. So bottom you have 1 plus 0.9. Okay, so 1.9c divided by 1.9. See, 1.9 canceled, give you c. So on the Earth, we measure the light, still give us same number. Okay. So now we go back to the example we discussed here. We put the number in the equation. See what we got. So if you throw a baseball at 0.7 c, and your motorcycle travel at 0.8 c, then you measure speed of baseball on the Earth. Does that give you 0.8 plus 0.7, 1.5 c? You know that's impossible. About that, but what's it going to be? We are going to calculate. Okay, so now the speed of the baseball relative to the stationary observer on the Earth's surface. Okay, the important thing you have to know which one's which. Uh, so we now see this figure here. So v equal to 8 because that's speed of the moving frame on the motorcycle. Uh, and u prime equal 0.7c because that's the speed of the object relative to the moving frame. And we want to find u equals what? So we plug in, use this equation. So u prime equals 0.7 speed of baseball relative to motorcycle plus speed of motorcycle. Then bottom we have 1 plus 0.7c times 0.8c. So you have c squared and cancel with this one. Okay, so that's why I see the bottom. 1 plus 0.7 and 0.8. C squared cancel. So now again we have a simple calculation. So that's 0.7c plus 0.8c, well 1.5c, 1.5. Now see the bottom, 0.7 times 0.8 give you 0.56. Okay, 7856, right? Okay. So now you have 1 plus 0.56. So that's 1.56. 1.5 divided by 1.56 will always smaller than 1, right? Okay, so use a calculator. 1.5 divided by 1.56, it should give you that 0.96c. That speed we measure from the Earth's surface. See, still slower than speed of light. Okay, so 0.8, then 0.7. It doesn't give you 1.5. Use this velocity of special relativity, give you 0.96. But we already discussed. It makes sense because this equation, okay, at low speed, going to reduce to the classical, right? At high speed, if speed equals c, will give you always speed of c, speed of light. Okay, so that's two examples. When you have time, you can review, and we're going to discuss more examples. We still have two more equations to discuss. Okay, so I will see you again next time.